Yo, all right, let's go. So, welcome to the next Ableton session. Today we're going to talk about synthesis theory, and synthesizer use with some very brief notes on music theory. Again, these are all topics that we'll go into more detail with in the future, like, specific topics like just music theory or more advanced levels of synthesis that we can dive into deeper in the future. But for now, let's start with a basic overview of, um, yeah, now that you've become familiar with using the DAW and its basic functions, the next topic is to discuss that of synthesis. So let's go over basics of theory of synthesizing sounds using a synthesizer and their use. So I'm sure, as you're aware, the root of creating sounds with synthesizers, understanding basic theories of sound synthesis will serve you well into the future as you create the sounds that you desire for your music. So to start, we'll cover the different types of synthesis and then explore each one a little bit. So these are the main types of synthesis that you'll encounter. And we'll start first with additive synthesis. So additive, as the name implies, is the method of putting multiple waveforms together into a stack to create complex sounds. As the method to create complex sounds, you're adding these waveforms together, hence additive synthesis. And it's often done using basic waves such as sine waves. And the method there is building harmonics by adding waves of different amplitudes, aka volumes. Amplitude, think amp, like guitar amp, amping, the sound is the volume. And this is the method of controlling the sound. So an easy example of this is down here in the operator synth. Again, here we'll pull up this classic, and you can see down here in the first oscillator we have open, it is a sine wave right here. And we have no filter on it, just the oscillator playing through the output. And you can hear one sine wave. But then we have a stack of 4 of them here. So as we turn on another sine wave, you can hear how that is affecting the sound. And then we have a third one. You can change the pitch of these different waves as well, then, of course. And stacking those together can be changed. The way you do that can be changed in this layout here. Now, this is actually the additive mode over here, where you're adding them together in a row like this. This is down in this output section, and you're changing the stack of the waveforms here in these different configurations you can click through that all give different sound results. Now, the pure additive form is this left to right being added together, where you can hear each individual sound wave together. If we turn these up, you can hear these different waves of different forms all being added together from left to right, like the output here. Turn them on and off and hear the results changing. And yeah, that is the method of additive synthesis, where you're stacking these waves together and then adjusting the amplitude, the volume of them, the different wave pitches and types and stuff. And yeah, it's a very old and classic synthesis model that is not used in modern music quite as much as the next one, which is subtractive synthesis now, whereas additive is stacking waveforms together to create a complex sound by means of their manipulation. Subtractive synthesis is reducing things from a complex sound source using tools like filters and different effects to create complex sounds. An easy and famous example of this, of course, is in Serum. And this is where you can use sound waves that have harmonic content and then reduce them with a filter over here, you can see. If we play that. So there, you have a full open harmonic sound source, and you're reducing it with the filter, or you're subtracting from it with the filter. You can also think of it using, like a notch filter. Here, you're subtracting this part of the this notch part of the filter. You're subtracting from the sound. And this is a really common method of synthesis because you are starting with rich harmonic material right away. Like you start with some, wave that has a lot of harmonics, a lot of sound to it, a lot of frequencies happening at once, and then subtract from that using your filters. And this is why it's like the most common synthesis method used in modern music. Again, simple, but all these different parts are the way that they are used and used in sequence to create the different complex sounds in music that we enjoy today. So the next example would be FM synthesis. Here, got another Serum example where FM is frequency modulation. This is the next most famous type of synthesis, basically. Frequency modulation is using one wave at audio rate to modulate the other, creating complex harmonics from the interaction. This is made famous by synths like the Yamaha DX7 and other 80s, 90s synths that found that they could create approximations of real instruments, aka brass, flutes, etc., by using FM synthesis. It creates rich harmonics and can be wildly crazy and is quite fun. So again, that's using one wave. So we have our first oscillator here being modulated by our second oscillator here. Now in Serum, this is set in this section over here. You select your source as FM, frequency modulation from B or from C, whatever your source is. Now this frequency is being modulated from oscillator B. And now this is different than modulating it with an LFO, like LFO being a low frequency oscillation, where the modulation produced by the low frequency oscillation is not occurring at audio rate, meaning when you have an oscillator that is turned up fast enough, the frequency is turned up high enough, it begins to actually oscillate and produce sound. And so that is what FM synthesis is based on. You can see here, this example, if I'm playing this oscillator being modulated by B, and we're increasing the amount of it here, sounds like first the saw wave, and then if we increase the modulation amount, you can see it creates a lot of rich harmonics from that, and it's all dependent on the information from the wave that's we're using to modulate it. So if I change that, it changes a lot. So that is modulating it at audio rate. Now the difference, like I said, the difference there is, what if I put an LFO on there instead and turn the frequency modulation off? Well, then we have the low frequency oscillator going like this. And you can see that going back and forth like that. We wouldn't put it on there. We'd put it on something like this is modulating the level of it with the FM source. So we'll put it on the level of this oscillator. and turn it all the way down and see what that's like at a low frequency. You know, it just turns up like this, and we can make that faster by increasing the rate of it. You can see it's down here measured in hertz, and the frequency, we're only at four oscillations per second here. But then if we turn it up, you can hear it moving like that. But then as we turn it up, getting close to audio rate, you can hear it begin to approach, you know, what is FM synthesis is like, but these only go up to 100 hertz, and that's barely within audio rate range. So that's the difference, you know, I'm just demonstrating with FM synthesis versus using, you know, an LFO for modulation. So yeah, FM synthesis, another very powerful method that is using frequency modulation. And then let's see, the next example, to wavetable synthesis. So wavetable is, again, example shown well in Serum, where you have this wavetable here that instead of playing just a basic wave, like a sine wave or something, a basic shape like a sine wave, instead of playing just a basic shape like that, it's using what's called a wavetable, which is a sound source. It's a sound wave that changes over time, and you can sweep through it linearly like this. This is using the wavetable position knob on Serum, and you can see that moves this line through and changes the sound like this as it moves. Let's see this here. So yeah, you can see that this is morphing through waveforms seamlessly, and it's a spread of a sound that changes from one end to the other. Like I said, Serum is well known for this, but there's a bunch of other synths that use wavetable synthesis as well. It's another famous method of complex synthesis because you are dealing with a complex sound source to begin with here. And then sweeping through it gives you a lot of very rich harmonic sonic possibilities within the many different wave tables that are available. So vector synthesis is another method that's similar to wavetable synthesis, but instead of sweeping linearly through a table, you're moving between four corners, often using a joystick that was made popular by some synths that included that. It is less common than wavetable synthesis, but it's quite similar and as well, and similar in function. That uses the movement in four directions instead of just back and forth, which is cool. But yeah, it's relatively similar in this way. So a note: many of these synthesis types, such as wavetable and FM, are then used in subtractive synthesis, shaping the harmonic content via subtractive methods like filters. As you can see in popular instruments like Serum, you're doing your wavetable synthesis or whatever you want to here, and then you are using subtractive methods here with the filter. And, you know, you can be using your FM modulation in that as well, all that kind of stuff. So there's FM synthesis happening here in a wavetable, and the subtractive part of it where you hear a very rich Rich meaning just a lot, rich harmonic content that then is being edited with the filter here. Yeah. Okay, last couple types of synthesis to cover briefly. One is granular synthesis. This is using small pieces of sound individually in different layers, patterns, and order, essentially breaking or fragmenting a sound into grains, as they're called, which can then be adjusted in size or number and manipulated to give very interesting results, unlike other methods. Granular synthesis is very common for abstract sound design, and it's quite different than typical synthesis using whole waveforms. Don't actually have a good demonstration of granular right now because I thought I had one in a Max for live instrument, but I guess not. So yeah, but it is granular. It's breaking a sound up into small pieces like grains of sand. And then different synthesizers will have different capabilities like moving these grains around, scattering them, changing their size, making them bigger or smaller. And it just it does yield really interesting results. Sorry that I don't have an example to show you right now, but that's something we'll get into in the future. Definitely do deeper dives into these methods. Like I said, this is just the kind of intro beginning to it. And yeah, granular. It's breaking things into grains, and then you will play with it in the controls the synthesizer offers that are similar to the other synthesizers we're covering now. It'll have filters and effects and different things like that as well. So the next common synthesis model is physical modeling. So this you can see here with this Ableton stock collision synth. Physical modeling, these are models simulating acoustic instruments such as plucked or bowed strings, pipes or percussion, things like guitar or violin or xylophone or marimba, that kind of thing. These model the attack of the pluck or strike of the instrument, striking the mallet on the percussive instrument, or plucking the string will have that attack sound to it of the attack of the initial pluck sound, and then the resulting sustain and decay of the sound fading off. And so these are all models that have been created to reproduce those characteristics, like this one here, this resonator type. You can see it's called a beam, and it sounds like striking striking a beam, like some metal bar kind of thing. You can change the model. Here's modeling a marimba. Changing the characteristics of it. String model. Membrane, like striking a drum head membrane. So yeah, you can hear it's using, it's often using combinations of FM synthesis, as you can hear this kind of very complex, almost like buzzy sounding, very complex frequency mixture that is reproducing the sound like the effect of hitting a membrane in this case. Now, these are controlled methods that are producing these, specific results, like modeling the instruments that they're going for. But this is a good example of how synthesis works. So all sound that we hear, right, is being created by some combination of sound waves. And we're familiar with the basic types of sound waves, like a sine wave, the smooth S-curve one, or a square wave, the one that's, rectangular looking, that kind of stuff. But technically, all sound waves are sine waves. They're just manipulated and shaped in different ways. A a saw wave, like you could see in a synth here. A saw wave like this, it's called a saw because it looks like the jagged teeth on a saw, for cutting wood kind of thing. Um, that that is just a let's go to basic shapes here. That is just a sine wave that has been shaped into these sharp angles. Um, See, you can, in the basic shapes, you could see them all lined up here and sweep through them actually. Sine wave, this is a saw, but you just can't see the ends, but imagine, it drops down, goes back to 0 in the middle on each end there. Triangle wave, a square wave, or what's called a pulse wave too, sometimes in different shapes, and then a just more uneven one. You can see that these are really technically all just variations of a sine wave, because a sound wave of an oscillator is it's literally an oscillation or a rotation of a wave of electricity, really, that spins fast enough that it creates sound. Like that's what's happening when you pluck a guitar string or you hit a piano key, which flips the hammer to strike the metal string inside the piano. The string vibrates and vibrates the air around it fast enough. It creates these movements, these oscillations fast enough that it actually creates sound. So that's what's so just mind-blowingly cool about synthesis, is that you are literally synthesizing, you are creating, from electricity, really, you're creating sound via the fast oscillations, the fast movements of these waves. Now, that plays into kind of the final example of main types of synthesis, and that's virtual analog modeling. Analog modeling is, as you might have guessed, it's modeling the behavior of an analog synthesizer. And it, again, an analog synthesizer, the analog to digital difference is that an analog oscillator is actually using like real electricity, like, the kind that comes out of your wall. It's using electricity, oscillating, spinning it in this oscillator, this little machine that is a real analog oscillator. It's oscillating, spinning this electricity fast enough to create this audible tone. And then by adjusting the frequency, the speed of these oscillations, which is the hertz, the cycles per second, a value of how fast that is spinning, is oscillating, that creates what we perceive as different pitches, higher or lower sound. So that's what makes analog synthesis special, basically, is that it's a real sound wave of real electricity that is being produced and manipulated to create this sound. Whereas digital, obviously, there's no lightning bolts of electricity firing inside your DAW in Ableton, right? So digital is recreating that, like I mentioned in an earlier lesson briefly about the sample rate, the audio rate in your program too. That's reproducing sound waves by essentially the same method as like pixels reproducing a picture. How a digital image is made up of all these tiny pixels, these tiny pieces. The same is done for producing sound waves digitally, where it's made up of all these tiny steps, these little bits, and that's your audio sample rate, is how many samples are happening, per second, where here we have our sample rate set at 44. So that's 44,100 little steps that are happening in each second to recreate the appearance of, like, the illusion of a solid sound wave, because even though it's technically these tiny little steps, we hear it like a solid wave, just like you see pixels put together as a solid image. So anyways, so that is getting into analog modeling. So another method of digital synthesis is modeling the characteristics of an analog synthesizer, which means basically reproducing the often unique or non mathematically exact results from analog instruments due to their use of real electrical oscillators rather than bits. You can imagine basically a real electrical machine that's producing a electrical oscillator, an electric oscillator. It's like a real live thing, right? So as you manipulate it, it's not always exactly the same the way that a digital version is. A computer, made up of bits and ones and zeros and stuff, is always going to do things basically the exact same way because it's always digitally exact with those calculations. So those exact digital calculations can also be made to replicate the kind of quirks and uniqueness and the way that the analog instruments are not always exactly the same. And so that's what instruments like this, stock analog synth in Ableton does. So, and it doesn't sound radically different or something. It just sounds like. It sounds very buzzy. Like you hear the comparing the sound of synthesizers is another topic too that is really just it doesn't really serve any purpose other than if you like the sound of the synth, great, then use it. If you don't, synths do sound different, but not like that really has a deeper meaning behind it. But you could hear like let's see, I had the just a basic sound wave set up here. Basic saw wave set up here, and serum. Does that sound? Oops, what's going on? Oh yeah. No, I have the saw wave here playing. I'm gonna compare it to the virtual analog one. I don't know. Maybe the virtual analog might sound a little buzzier or something, or the sound may be a little bit different in some ways as it tries to replicate the unique characteristics of the analog instrument. So yeah, those are the basic main types of synthesis that you'll encounter. There are a few other really niche ones. There's also sample-based synthesis, which is very similar to wavetable synthesis, again, where you have that three-dimensional, what looks like 3D wavetable, the table spread out of a rich sound source. You can basically do the same thing using a sample of, anything. Any sound sample can also be used essentially as a wavetable, basically, and that's called sample-based synthesis. Yeah, so that is the basic walkthrough of different types of synthesis that you'll encounter. Like I said, remember, most of it is used in conjunction, like you have your wavetable using some FM or something with subtractive tools like filters being used in combination. So using a synthesizer to illustrate that as well, you are familiar, of course, with the oscillators we have pointed out here. We're using oscillator A, oscillator B. Serum 2 has added a third oscillator, C, here. Those can all be mixed together with their levels here and their different blend. And then they also have a noise oscillator here. And again, don't worry about the fact that this is Serum, you don't have it or whatever. These are all basic parts of a synthesizer that you will encounter in different forms on basically any synth. They're all unique and different and stuff, but these are the basic functions that you'll find that are universal. So noise oscillator. It's just an oscillator that is playing noise instead of white noise or pink noise instead of a sine wave manipulation. So, and those are all mixed via their levels here. You have different controls over them. Like I said, these are the manipulation, modulation sources you can set to different things in the oscillators here. This is the unison control. Here, unison is going from one sound here. You can see one. You turn up the level. Then if we go up in unison, yeah, that's the super saw. If you wondered how to make a super saw, that's it. You put the unison up. Yeah, so detune. Detune, you can see, is detuning, moving those unison oscillators against each other. Is detuning them, very common in kind of more avant-garde sound design, like in IDM and stuff. Blend is changing how those unison sine waves are blended together, or sound waves are blended together. Panning, left and right panning, of course. And yeah, the wavetable position where you can sweep through the wavetable. And yeah, then you have envelopes down here. Now, if you recall, an envelope is something that gets triggered when you play a note like this. And you can see me changing the shape of the envelope, which in this case is automatically routed to the level of the oscillator, so it's controlling the level. And as you adjust the attack, hold, decay, sustain, release, the different parts of the envelope, that changes the parameters of the sound you're playing. So the attack, now that's the initial beginning part of it. The attack, if it's a fade in like that, or an immediate, attack. The hold is the amount that the sound is held at the top here before it goes into the decay, which is the decay, the fade out, the decay of the sound. And the sustain is how much the sound sustains once it goes through the decay. You can hear it sustaining at that level via, if I turn it down, it would sustain at 0. And the release is a final, it's like a final decay stage after the sustain, like this. Once you let it go, then once you let the sound go, you can see it traveling down the further part here. And then it releases, and then it releases in the last release section that you can adjust. So that is adjusting the envelope. These envelopes, like I said, they're the first envelope in this synth, and most synths you'll find are automatically routed to the level, playing the volume, the level of the oscillator that you're triggering. But they can also be set to other things. Here in Serum you have like 4 envelopes, and you can set them to other things. You could have it, triggering you could have it, the envelope triggering. The envelope is think of something. The envelope is something that's triggering something when you're pressing a note. Whereas an LFO is something that can just be set to do something. Like, as you play the note, the envelope happens. The envelope happens when you trigger the note, but then the LFO just continues to play, continues to cycle. And you can adjust the rate of the LFO here, either in hertz or synced to the BPM. You can adjust the shape of the LFO here. You can draw your LFO shape in a lot of synthesizers like this, or you can select the standard shape. Like a lot of LFOs will come, in like a sine wave or something shape, where the LFO just travels up and down that sine wave, which, by the way, is a good example here. With these points, you can see how this cross through the middle of a visualization of a waveform here is important. The horizontal line in the middle here is considered 0, like 0 dB, like no volume, like level turned down Like that is called a zero crossing. And so remember I said the sound waves are actually, they're oscillations. So they're actually, um, they're oscillations or, spinning of a wave at a rate that's fast enough that it actually makes sound. So, but how do you illustrate that in a 2D representation, right? Drawing a circle doesn't really, of this, the circle oscillating doesn't really tell you that much. So it's basically split down the middle like this. You could think of, imagine that this half over here is actually, it's right underneath this. It's actually making a circle like this. Um, but it's spread out in this way to illustrate the three-dimensional, plane on a 2D thing like this. So as the sound wave starts spinning from this zero crossing point here, it spins around in a circle, and then of course it would actually be spinning back in the circle as it oscillates like this. But it's shown here, split up so you can actually see and manipulate the sound wave in this way, that it continues on this other side before going back up to the 0 point. So this 0 point is the same. This point is this point over here. And that's why when you see it playing through an LFO, which I think you can, yeah, you see the play bar here going through it. That's the representation of it actually, spinning around, oscillating like this. And it's actually more of, I mean, it's kind of more like actually like a spiral thing, because the sound wave actually does travel. The sound wave does actually travel up and down over distance as it goes through the air and hits your ears. If you're not familiar with that, the way we perceive sound is by these waves actually physically hitting the hairs in our ear, essentially, which triggers the response in our brain of what we perceive as sound. So these waves do actually go up and down like this as they move through the air, literally, but they are also spinning and oscillating, and so that's what this shape actually means. And that's the same thing you're seeing up here, starting in the zero crossing point here, going up to the peak of it, and then it drops back down to the minus peak, the minimum peak of it, the opposite side, before coming back up to the zero crossing point again, which is the same zero crossing, starting point. And so even these complex waves that look like this, you can see they're doing the same thing. They're starting here, it's doing the buzz thing that goes, and then it crosses the zero over here again and goes back up, and then comes back in the zero here, which is the beginning here. So that's what this all means, and that's where you can adjust in the LFO what that oscillator looks like. And that's the same thing, as you can kind of see, that's how this sine wave is being manipulated to come up with something more complex, just like this complex wave up here. And as it flows through the variation of those, you can see the wave changing as it flows through, a real different variation in the wavetable. And you can see then it's giving you really complex sounds. Yeah, complex wavetable sounds that are very rich in harmonics, meaning these are all these little points and all these manipulations in the wave, everything that deviates it from this nice smooth, wave of the sine wave, is all considered like harmonic content, stuff that you hear, harmonics. And so these really rich harmonic waves like this are very popular in electronic music. Essentially, it's how people make, crazy dubstep and stuff. You have a very harmonically rich sound, that buzzes really loud, and then you chop it up with a filter to make it, uh, do stuff. Um, why am I not playing this? um, yeah, and it come on. Um, it does this. You have this harmonically rich, sound source like this that what's going on? Oh, no, what am I doing? Anyways, yeah, you have a harmonically rich sound source that is being chopped up with a filter like this. I don't know, what did I do to that? I'm not taking the time to figure that out. Yeah, so if you have a wavetable like this, and again, you're scrolling through. Oh, next section, the filter. You're often probably familiar with what a filter is, but filtering the sound, and you can choose your different filter shapes here, either a low pass, meaning that the low end of the sound passes through over here, versus a high pass, where the high end of the sound, the high frequencies pass through. And then you have lots of different other filter shapes, like bandpass or a niche or a notch. I mean, different things. Like a notch is just a notch in the filter like this. Yeah, back to what I was just saying before there about having a harmonically rich sound source like that, and then cutting it up with a filter to get something like putting the LFO on the filter to get that rhythmic chopping of the sound is a very common technique used in things like dubstep, where you have a sound that you have a loud, like really you have a loud, very harmonically rich sound like this that you wouldn't really want to hear play for sustained periods, but then you chop it up into smaller bits with the filter, and yeah, that's what they're doing essentially. So, okay, I know I said I would touch really briefly on. Oh well, okay. Sorry. Let's finish the parts of the synthesizer first. Okay, what else? You have your sub oscillator over here. I explained that before once briefly, but sub oscillator is just an oscillator that is tuned to be an octave lower or higher from the, or you can change it here, but it's a sub oscillator. It's generally just playing a solid wave, like a sine wave, to add sub bass to your sound, as you can hear. And yeah, the mix of all these oscillators is done in this section, which then is coming into the mixer section that synthesizers will usually or often have, where you can adjust all of those mixes again, the levels of things that you're hearing. And going into the filters and coming out of the filters, and the mixture of the different sources in the synthesizer. And then the FX section, where you can add effects to it. You can add things and adjust the, mixture of it here. You can just use all of these to change the sound, obviously, and each effect has its own, characteristic, a thing that it does, and way to operate it and use it for different purposes. Yeah, the FX section, and then the matrix section. This is where the matrix, the modulation matrix, this is where you have all your modulation sources, and you can just another way of dealing with them other than, this click and drag method in Serum kind of matrix, where you have your source here, the amount that it's being used, and the position of whether the polarity of whether it's going, one way or back and forth, or only one way, like turning from 0 to full, or going from 0 to minus full, back to positive full, back and forth, positive and negative. And then the destination of where it's going, where you can also change your, you can add other sources like your controls on your MIDI keyboard, etc. And yeah, this is the modulation matrix, where you can just adjust all that stuff. You could say, I want another thing to come here, the LFO3, or I could use oscillator B to change, something, filter 2, frequency or something. And you could just change all those things and set them here. And then global settings. This is where you adjust synthesizer global settings, like the tuning, frequency, etc. You don't really need to worry about this. Honestly, this is just for some very specific details you might want to change about something. But yeah, those are the basic parts of a synthesizer. Down here, you've got a representation of a keyboard. Of course, your portamento or glide, which is just that kind of like glide between two notes when you play two notes. This is the adjustment for that here. The voicing section of a synthesizer, if you have a mono synth only playing one note at a time, or if you have a poly synth that can play 8 notes, 16, 18, 24, 32 notes at a time, you can adjust that here. And that's poly, how many notes you can play at once, poly, versus mono, one at a time. So you've also got controls over here for a mod wheel and a pitch bend, which is, bending the pitch, and the mod wheel is another control you can set to control something, like in that matrix, you could select the auxiliary source of a mod wheel here, and then, to a source, to a destination, destination here. Yeah, Serum has macros. These are unassigned knobs that you can set, like just click and drag and put on something, and then now that knob controls whatever you put it on. And then in Ableton, if you want to map that to something using a third-party synth like Serum, you will use this control down here next to the power button on the plugin. There's the little arrow. And again, remember, info tab, keep the info view open, and it tells you all this stuff. Unfold the device parameters, click that, and that opens up the device here. And then you see this configure button here. You can click configure, and it turns green. And then whatever you click on the synthesizer will show up here, like that. And then when you're done, click configure to turn it off. And then you have controls over your synth. You can see like that macro knob spinning here. When I adjust this, that's how you get the controls of a synthesizer, of a third-party plugin, not a stock plugin. How you get the controls of that into Ableton to then right-click, show automation, and then do your automation modulation for that. So, and of course you can also group it. Right-click, group, and open up the knobs and map those things to, map them to the knobs there and use it that way. So you have that control scheme set up again in Ableton. Yeah. Yeah, of course you can do that as well. So, yeah, basic synthesizer operation. Now remember what I said, I'm using Serum as a demonstration here, but all of the basic parts and functions, if you familiarize yourself with them, you will recognize them in other synthesizers because they will be in different shapes and forms, but they're the same core functions of synthesis. So an oscillator being manipulated somehow, being manipulated by an envelope and by modulators such as LFOs, and then flowing through into a filter, and then going out into a mixer, being adjusted in a mixer, passing through effects, and yeah, coming out the main output up here. All synthesizers are going to roughly go the same. And so the point of going over all this, is the more you familiarize yourself with the basic concepts of synthesis and how it all works, you'll begin to understand, like, oh, wait a minute, I want this kind of sound, and how do I create that then? So then you're not just clicking through presets randomly trying to find something that sounds like what you want. You have an understanding of, oh wait, what does that sound like? Does that sound like a does that sound like a buzzy sine wave, or a saw wave or something, or a smooth the smoothness of a sine wave, or I have effects on it, but now, yeah, like the smoothness of a sine wave, or the buzziness of a saw wave, etc. This is manipulating like that. Yeah, you get to understand the different waves. Oh, there we go. Or like the distinct sound of a square wave. Stop that. You hear that distinct kind of almost like tubular, 3D sound of a square wave versus the smoothness of a triangle wave or a sine wave or the buzziness of a saw wave, etc. You begin to recognize these different sound characteristics and understand what they sound like and how to combine them together into the sound that you're kind of looking for. So yeah, presets are a really good thing to load a preset and find something that you want and see, oh, how did they make that? But then reverse engineer the preset, go through it and see, well, what did they do there? How did they set that up? What kind of oscillators are they using? How are they being manipulated? What's the modulation LFO doing? What about the filter and the effects and all that stuff? Yeah, reverse engineer presets is a good way to understand how different sounds are made. But yeah. Okay, and then last I said I'd have a final, like a brief mention about music theory. So music theory is, again, one of those topics that you can go on into great depth for at length. People spend their whole careers and, professionally studying music theory and academia and all that stuff. But when it comes to producing music and having fun with it, I think it's really good to not overthink music theory and just remember that when you're playing notes together, you just want to listen to how they sound together. And one simple tool that you can use to do that, to kind of help you, there are a lot of tools out there, but you can use something called the circle of fifths. Now, this is a common tool used in music theory to illustrate conventions. It's the circle of fifths. It's all the notes in the Western 12-tone musical scale that we use set up here, and then across from it, it tells you the corresponding notes that go with it. You can find simple explanations for how to use the circle of fifths. I'm not going to go over all that right now, but the main thing to keep in mind is that it's fifths, right? So to demonstrate what that's talking about, we'll use the piano roll here, or the piano key, demonstration on the bottom of this serum here. And if I play a note of C, now let's go to init. Okay, I'm playing a C, right? You can see that note being triggered here. And then if I go 5 steps, a fifth, if I go 5 steps up from it, so 1, 2, 3, 4, 5, that's an F. And if I play those two together, you hear how it sounds? It sounds nice, right? Because those two are a natural complement to each other. That fifth step up from the note fits as like it's like a whole complement to that specific note. And then you can do that again from F. Let's go up, 1, 2, 3, 4, 5. Play that together. You hear that? Okay. Now a fifth isn't the only musical interval that's called the space between the two notes. It's not the only interval you can play, but it illustrates the idea that if you're trying to write a melody or use notes and figure out the music theory for the song you're making, you just want to figure out if the notes you're playing together sound good together. Because how does that sound? Like the C and the F together? That fits. It sounds good. But if I play different notes, like another one, now you hear how that sounds different, right? Now that means that you don't want to play those two notes like in a chord together. But that doesn't mean you can't play those two notes, the C and the D together. You hear those two notes separately, or even like a half step. This is the black key in between. It's called a half step between the major the white key notes like that, and then half step. But you hear how that half step together, if you play it together, yeah, it sounds what they call dissonant. It doesn't sound good together. But those two notes separately, well, there you go. That's like so many drum and bass tune, bass lines, just going back and forth from, that kind of thing. So it's all about the relationship of the notes you're playing and do they sound good together in the way that you're using them. I mean, as jazz illustrates quite well, there really are no rules about what you can and can't do. The only thing that really matters is if you are achieving the result that you want. If you think that these two notes sound good together in your song, well, that's fine. Then make that, no one's going to stop you. But you hear how it sounds if I'm playing a C, like for example, playing a note, and then I just play other notes and hold it along with it. You can hear how that sound changes. That's a good way to play around with notes without knowing anything technically about music theory and music notes and, circles of fifths and intervals and all that stuff. Just find a note, say like, well, I want to make, well, okay, I'm using C because what's called middle C, this C3 note here, is considered, it's the middle of the keyboard, and it's just considered the kind of, the middle, like zero starting point for, musical notation generally. But honestly, the key of C, I mean, you can totally use it, but the lowest note of C is like it's too low to translate into clean and audible sub bass lines. So people often don't use it in electronic music. They go to at least like a D, or something a little bit higher that's just a little bit easier to hear at those low notes. So I'll use E as an example, instead. But then so basically you figure out like, well, what key do I want my song to be in? That means, the key, the dominant note. Do I want my song to be always resting in the key of E, or maybe F instead? So, you can figure that out. And then once you have, that say like, okay, I want to make a song in F or something. Well, then play some different notes with it. And you kind of get an idea of like how these different notes sound together in relationship to each other, right? Like this. Well, that's what they call a major key, happy major sounding, as opposed to minor sad sounding, right? It's those kind of basic choices you're making, which will just change the feeling of your song if you're going between, these notes of versus, those obviously give you very different feelings in your music. So once you've chose, you're thinking about that as well. And like I said, I'm just holding notes and playing them together and seeing like, well, like, oh, that sounds cool. What is that? That's really is what I'm trying to demonstrate is that you can figure it out by just playing and trusting your ear. I know a lot of you are DJs as well, and or just at least music listeners, and you can recognize something that sounds good to your ears versus something that doesn't sound good. Like this. You can see, oh, well, that sounds cool versus like, oh, that doesn't sound good. So just trust your ears and play around in that sense. And you can read up on things like the circle of fifths that help you understand, some of the theory that you can begin to begin to figure out yourself. But as a really good starting point, I just like to talk about playing notes like that and playing notes together and figuring out how they sound and what sounds good together and what doesn't sound good together, And like I showed, you can play these two notes back and forth together and think, well, how does that feel? How does that sound? Is that the feeling and the sound that I want for this track, or is it not? Like with the demonstration of playing the minor key versus the major key, this major key versus, those are very different feelings. If you play the major key versus, now let's say if you're those are very different feelings for your song, depending on what kind of vibe and feeling you're going for. So just by playing those together, you can figure that out. Is that what I'm looking for or not? So that's a good starting point with music theory. I'll do more specific, in-depth lessons about that in the future. Same with synthesis, but this is the just next intro session we're getting into about more thorough understanding and use of your synthesizers and instruments and the notes you're playing into them and why. That all build on the stuff we've been covering up to here. So, yeah. Are there any questions or anything people want to ask at this point, stuff I could cover? If you have a question, ask away. Otherwise, of course, this is going to be recorded and available to view in the future. And if you have any questions that come up about synthesis topics or music theory, music notation and stuff, you feel free to ask. So, all right, well, I hope you've enjoyed our little session here. If there aren't any further questions, I'll see you guys in the next one. All right.